Thank you for coming in today. It's an absolutely beautiful day. It's a shame to spend it in a cave, but I hope that I'll make it worth it. But those of you who came last week, how was Lee?
Very good.
Very good. You guys learned a lot about detectors. Ask all of your questions that you've been asking me for a couple weeks now that I can't answer. All right, good. All right, so today I'm going to focus on gravitational wave sources. So we've spent the last few weeks learning about special relativity, general relativity, and how we can get gravitational waves. And now today I'm going to focus on what emits them. For those of you who haven't been here yet, I like to encourage questions throughout, so please don't hesitate to interrupt me. And if we end up getting off track too much, I may push questions to the end. All right, so one slide reminder on general relativity. You have a mass. It causes a curvature in space-time, and other masses feel that curvature. So space-time tells matter how to move, and matter tells space-time how to curve. This geometric description of gravity is pivotal to understanding what gravitational waves are and what can create them. This is a kind of cartoon picture of a sun-Earth system. We just in general will call it a binary system, and that kind of system is capable of creating gravitational waves, amongst many other things. So, to get gravitational waves, according to general relativity, we need this time-changing quadrupole moment. And so what that really means is that you need to have this time-changing non-spherical component to some distribution of mass. So you generate these ripples in space-time with those time-changing non-spherical movements of mass, and that creates these ripples that travel at the speed of light, according to general relativity, and are unimpeded by matter. And those will propagate through space to get to us and our detectors, where we hope to measure them and learn about the universe with them. So here we have a spherical star, looks like the sun. Does anybody expect this to emit gravitational waves just sitting statically in the universe?
No.
No, right. No gravitational waves from a stationary star. Now let's rotate it. What do you think, gravitational waves?
No.
So I heard it's a no and the answer, then you're both right. So if it's a spherically symmetric star, so it's a perfect star, any rotation it has won't cause any gravitational waves. If there's some asymmetries, then maybe that will be different. And now it blows up. That's a pretty energetic event. Supernovae are incredibly energetic. Lots of mass moving around. Do you think this will create gravitational waves?
Yes.
So I think I heard some yeses and some no's. Both are right again. If it's an exactly spherically symmetric explosion, it blows up in a sphere moving outwards, there will be no gravitational waves emitted. You need an asymmetric explosion to create gravitational waves from a supernova. So here is a computer simulation, and what this is showing, so this is purely numerical, it's just a simulation on a computer. A supernova is the explosion of the very center of the star, where the nuclear fusion has built up the heavier and heavier elements until it runs out of things to burn. And then you can no longer support the star, and it gravitationally collapses to the point where it triggers a new explosion at the very center, and the details of that explosion are what decide whether gravitational waves will be emitted or not, and whether they're going to be strong enough for us to detect. So when it explodes, there's an asymmetric explosion, where it has this preferred channel through the star, where the explosion travels all the way to the surface and then exits the surface of the star. That will create this asymmetric explosion, this non-spherical movement of mass that we need to be able to get gravitational waves out of such an event. Now that will also cause kicks, which is very interesting from an astrophysical perspective. If we can measure the kicks that these supernovae give when they explode, we can learn a lot about the details of the interior of these stars. All right. So now, instead of single stars, we have two stars. This is a stellar binary system. And this will also create gravitational waves. So here are those nice ripples traveling off throughout space. You'll notice if you look at the very edge here of that little worm, you see this plus kind of motion. You can see an expansion in the up and down direction, where there's a contraction in the left and right, and then it alternates. There's an expansion in the left-right direction and a contraction in the up-down direction. So that is one particular polarization of gravitational waves. There's a complementary polarization, which is if you get that same pattern and you rotate it by 45 degrees, and that's a cross kind of expansion and contraction. And so in general, it's just like light. So light has two polarizations, an up-down and a left and right. And polarized sunglasses, for example, work by blocking one of those polarizations. If you have light reflecting off from some puddle on the street, it preferentially polarizes light. So if you block out that sideways polarization caused by glaring sun, then you can see and you don't get blinded by reflecting light in ponds. Gravitational waves have the same thing. They have two polarizations. They're off by 45 degrees instead of 90. But they're two completely independent channels for us to get information about the system. And so that will be important in a later lecture where I tell you how we learn about the actual sources of these gravitational waves by measuring their signature. Any questions yet on the production of gravitational waves in this kind of cartoon picture?
Why would it be 45 degrees?
Because if you have, it's a strange result of this quadrupolar source of gravitational waves. So you have this plus shape. If you imagine rotating it by 90 degrees, you just get that same plus shape, right? The only way that you can get this kind of oscillation in a plus or cross direction is if you rotate by 45 degrees. That's the only way you get unique motion out of space. But it's a rather strange thing to have a 45-degree rotation, but it's just because it's this quadrupolar type of emission. Yeah?
Why do you need asymmetry in order to see gravitational waves?
So the asymmetry is important because it's also going back to that quadrupolar thing. So part of it is because gravity doesn't have a negative. So we can get dipolar radiation. So you can get, you have a monopole, a dipole, a quadrupole is how you do this multiple expansion. And so by saying that we need quadrupolar emission for gravitational waves to occur means that the monopole and dipole things don't exist. And we have dipole radiation in electromagnetism because we have a plus charge and we have a minus charge. So you can create this dipolar radiation. But because mass is only positive, we have to go to the next step up. We have to go to this quadrupolar form to get radiation. And so the details of how that actually comes out is all just in the equations of solving Einstein's relativity in a linearized sense to get this, to get the first term that actually radiates these waves that we're looking for. But the short answer is because mass is only positive. Any other questions? All right, so let's get to sources. I've listed here 6 different sources. We have man-made sources, things in the solar system, and then things that may be a little opaque right now, but I'll go into more detail. Continuous waves, compact binary mergers, burst sources, and stochastic. So these are all maybe potentially sources of gravitational waves that we can hope to detect with LIGO. So here's that gravitational wave strain equation again that I've been showing a lot. So just to remind you what this is, H over here on the left is the strain. That's the thing we're trying to measure with our detectors. That's the amount of stretching and squeezing of space-time. So in our case, we have our LIGO detectors, this L-shaped building with 4-kilometer-long arms of the L, and what we're trying to measure is this change in length of those detectors divided by their overall length. So it's a delta L over L. It's change in distance over distance. So this is a unitless number. And then we have these units here, this 2g over c to the 4th. This r here is just a distance to the source, it's a distance between us and the source, and that makes sense because if this distance gets big, it's in the denominator, so it makes that strain small. So if we get too far away from the source, the amplitude is going to be too small for us to detect. And then finally, there's this I here with 2 dots, which means we have a quadrupole moment. That's the thing we're looking for, time changing. And then those 2 dots means 2 time derivatives. So that means an accelerating movement of this non-spherical component of the mass. So the important thing to really note here is that term that I quickly glossed over. So that's 2g over c to the 4th. C, the speed of light, is a big number. G, the coupling of mass to force, is an incredibly tiny number. So you take a tiny number and divide it by a huge number to the 4th power, you get a really, really, really tiny number. And that's what that number is. It's 10 to the minus 44. It's a crazy tiny number. So that means that if we want to have any particularly big strain over here, that I double dot, that time-changing non-spherical component of the mass, has to be huge. Absolutely huge. Yes?
I would expect there to be an r squared in the denominator.
Yes, so r squared, an inverse r squared, is a very, very common form of mathematical equations in physics. So gravity falls off like 1 over distance squared. Electromagnetism, the energy that we can measure, falls off like 1 over distance squared. This 1 over r squared law is a very common feature in physics. This is 1 over r. And that is because instead instead of like in electromagnetism, the thing that we can actually measure in electromagnetism is energy, which is an amplitude squared. In gravitational waves, we measure the strain, not the energy. So we measure the strain of the gravitational wave, which is just 1 over r. And so we don't get that extra power of distance that is common to most laws, which is actually very helpful for us because we're trying to detect these things. And if we fell off like 1 over distance squared, it would be impossible. All right, so gravitational waves generated by this non-spherical, time-dependent distribution of mass, and it's multiplied by an incredibly tiny number. So how are we going to get gravitational waves out? We're thinking about man-made sources. One thing we can do is just take 2 very large masses. We know that this kind of binary star type system will create gravitational waves, the non-spherical distribution of mass that we can move around. So let's create one on Earth. If things are going to be falling off like 1 over distance, so why look for distant things when we can just make something here on Earth next to our detector? So here is a type of experiment that has been conducted in the past. Take 2 very massive objects, say around the mass of a car. You put them on some beam that's about 10 meters apart, and you spin. And so this is 10 hertz. Sounds like a pretty low number, so that's 10 cycles per second. It's not very slow for rotating 2 cars in a circle. You spin them around at 10 hertz. That will create gravitational waves. The gravitational wave frequency is directly proportional to the rate that you're spinning those cars around. It's actually a factor of 2. So if we spin these cars at 10 hertz, at 10 cycles per second, then we get gravitational waves out of 20 hertz, 20 cycles per second. And so create these gravitational waves, excellent. And that's what we're trying to measure, that strain, that change in distance over distance. And I think that number's going to be big or small for this experiment. Tiny. So 10 to the minus 43. And for those of you that remember the strain of the gravitational wave event that we just detected and announced in February, it's 10 to the minus 21. So we're only 20 orders of magnitude off from something that we can actually detect on Earth. So I saw a question in the back.
To the extent that the science can say what electromagnetic waves are made of, what are gravitational waves made of?
So you mean electromagnetic waves thought of as photons?
Yes, so how would you define what gravitational waves are made of?
So there's a complementary particle to a photon, which is the carrier of gravitational waves in some theories, the graviton. And so you can have wave-particle duality, much like electromagnetism, between waves and photons. You can have that with general relativity, where you think of these ripples in space-time as being these waves, and then the particle component of them is the graviton. And then there's alternative theories of gravity that try to give mass to this graviton. So in any theory, according to special relativity, if you have something that moves at the speed of light, it cannot have mass. So photons are massless particles. Neutrinos are incredibly energetic particles that move at almost the speed of light, but not quite. And because they don't move at exactly the speed of light, they have just a little bit of mass. And so we can detect those in very different ways than photons. So alternative theories of gravity can sometimes assign mass to this graviton, which would make it travel at not quite the speed of light. And that's a test that we can actually do with LIGO by measuring the overall signature of these gravitational waves, the exact morphology of how they travel through time and frequency when we measure the detectors. Measure them in the detectors.
Thank you.
Yes?
Do gravitational waves travel at the speed of light?
According to general relativity, yes. And according to the measurements that we just made, as sensitive as we can be, they seem to travel at the speed of light. So the effect of gravitons not traveling at the speed of light, or gravitational waves not traveling at the speed of light, would be this dispersion, where you have different frequencies of the gravitational wave travel at different speeds, which is what happens when you have mass particles. And if we look at the exact morphology of the wave, at how it chirps up, if the graviton were very massive, that chirp would get all distorted because it's going to different parts of the chirp are different frequencies, and they would travel at different times. And so you see the very end, the highest frequency component, become before the earlier parts, which are lower frequency. And so we aren't, according to general relativity, gravitons don't have mass, and so therefore gravitational waves travel at the speed of light. But alternative theories are still valid based on the measurements we've made. We have to make more sensitive measurements to really constrain them. All right, so man-made sources, at least this one that we dreamt up, impossibly tiny gravitational waves. We're never going to see those. So let's cross those off as LIGO sources for now, and look to the solar system. Anybody imagine what create gravitational waves in our solar system?
rotation of the planets.
Yes, rotation of the planets. So, particularly Jupiter. Jupiter is the bully of the solar system. It affects the orbit of all the other planets in a very measurable way. So, the Sun-Jupiter system is kind of like a binary star system, just with a very asymmetric distribution mass, which is great. Okay, so then let's think about what the gravitational waves from the Jupiter-Sun system would look like. So, first of all, we can't think of them in the classical sense, or in the sense of these ripples traveling in space-time. And that's because we're actually in the middle of this system. So to describe gravitational waves like I've been doing throughout the lecture so far, we need to be in this far field limit, where our distance from the source is much bigger than the overall wavelength of the gravitational waves that are being created. So since the gravitational waves that are being created, the wavelength is decided by the separation of the masses in this case. Since we're inside of this system, that we can't describe gravitational waves in the same way. But instead we just think about the type of energy, the amount of energy that's being created in gravitational waves. That would carry energy out of the Sun-Jupiter system, and when you take energy out of an orbit, it shrinks. So even if we can't measure the gravitational waves directly from the Sun-Jupiter system, maybe we can see the orbit shrinking because it's losing energy in these gravitational waves. And so when you go through the equations, you calculate the number, you get about 5,200 watts of energy in gravitational waves is created. So that's power per unit time. And light bulbs, old light bulbs, not new light bulbs anymore, were 60 watts. This is about the typical power consumption of a U.S. household. So it's the coupling of gravitational ripples and energy to space-time is incredibly poor. And so having tiny energies like this make it impossible to detect gravitational waves. So solar system's out, yes?
Was it a measured number or a purely theoretical?
This is a purely theoretical number. And because it's so tiny, it's probably going to stay that way. We are not likely to measure the gravitational effects, the gravitational wave effects from the Sun-Jupiter system. And that's the biggest generator of gravitational waves in our solar system. Okay, so that's out. We lost out on Earth, we lost out on the solar system. The only thing left to do is go to bigger scales. Galactic scales or intergalactic scales. So that leaves us with these other four sources that I've been mentioning before. So continuous waves, compact binary mergers, bursts, and stochastic. Now this division is a little bit arbitrary. This is what we use internally in the collaboration to separate out the kind of sources we look for, the kind of gravitational waves we look for. And their separation is as much motivated by the actual physics of the source as it is the gravitational wave signatures and how we look for them. So, alright, the gravitational waves created within the solar system, both on Earth and on the Sun-Jupiter scale, are pretty unimpressive. So let's go to more impressive things, and some of the most impressive objects in the universe are neutron stars. So neutron stars are the final, for those of you that came to a lecture series I think a year ago, we learned all about neutron stars, right? So neutron stars are these incredibly compact objects. They're the end they're the end of the life for a certain range of masses of stars. And it's the leftover core that's basically one gigantic atomic nucleus. The density of this thing is about nuclear density. So it's about the density of the nucleus of an atom, which is insanely dense. They typically have masses around 2 times the mass of the sun, so 2 solar masses. That's the most massive one that we've measured so far. And the size of them is incredibly tiny. I mean, these are really compact objects. The typical radius is about 7 miles. And so you're cramming a whole lot of mass, 2 suns of mass, into a 7-mile sphere, or 14-mile sphere, if you like to think of diameter. So there's a little bit of perspective. That's what the imprint of a neutron star on the Chicago area would be. And so if you put the center of the neutron star right in the loop, you basically get the surface of the star to be around the University of Chicago. So you can bike the full width of the neutron star if you have a lot of energy. And so just in case, the mass of the sun is also kind of hard to interpret. So that's about 600,000 times the mass of the Earth. It's a lot of stuff. Okay, so incredibly dense material. And how dense is it? How can we put that into perspective? If you were to take that neutron star, take some matter off the neutron star, fill this 12-ounce bottle with it. Anybody guess how much it would weigh? Order of magnitude. It's about the mass of Lake Erie. So you put the entire mass of Lake Erie into a 12-ounce bottle, And that's how dense the matter is in a neutron star. So this is a great place to try to look for gravitational waves. It's incredibly compact. We're at the extremes of physics, right? Like the extremes of what the universe can produce. Maybe that will be able to create gravitational waves that we could detect on Earth. So we know neutron stars exist. We see them all around the universe. They have, mostly all around the galaxy. It's actually hard to detect them in other galaxies just because they're so far away. But this is a typical picture of what we think a neutron star looks like. We have neutron stars, because they're so dense and they have magnetic fields, have this magnetic field, just like a typical bar magnet that you see. So it's got a north and a south pole to that magnetic field, and that typically has some misalignment with the axis of rotation. And when that thing is rotating, and it rotates fast usually, you have emission going along the magnetic poles, rotation going along some other pole, and so you get this lighthouse kind of effect as the neutron star rotates. And if we happen to be lucky enough to be somewhere along the path of that beam, we see these very, very, very regular pulses of radio or X-ray emission. And so here, there we go. All right, so here is measurement, slowed down greatly, of the Crab pulsar. And for those of you who aren't familiar or have seen this picture before, it's a very famous picture from Hubble. This is the Crab Nebula. So there was some supernova explosion that happened within recorded history. This is the remnant that we see of that explosion, and in the very, very center is this neutron star that we see emitting this very, very regular pulsation that you can see down here. And so the frequency of that pulsation is 30 hertz, 30 times per second, so you can imagine how slowed down that is. Okay, so we have this very quickly rotating neutron star. If there's some asymmetry, it will create gravitational waves. So if it were perfectly spherically symmetric, we already showed that that rotating star doesn't create any gravitational waves. But if there's some asymmetry, this is such a dense, extreme environment. You can think of these little irregularities. They must have some kind of effect, and it's actually a pretty reasonable effect that we can hope to measure. If it does have some asymmetry, here's the gravitational wave we would expect, measured by LIGO. And so this is basically a sine wave. It's just a single fixed frequency in gravitational waves, just a hum out there at a distance. The frequency, again, is twice the rotation frequency of that star. So the Crab pulsar rotates at 30 hertz. The gravitational waves are emitted at 60 hertz. And so I was having a sound issue, but I came here an hour early, and I couldn't get the sound working. So that's a bummer. But if you listen, that's what the gravitational waves, if we convert to sound from the Crab pulsar, would sound like. So it's a single sine wave at 60 hertz. Now, does anybody know what else happens at 60 hertz? Yes. So in this case, the universe was very unkind to us. It put the gravitational wave frequency at exactly the power frequency, at exactly the frequency that AC current goes to all of our instruments. And so if we look at the sensitivity of our detector, we get really, really sensitive. The noise gets to very low amplitudes around as we get to 60 hertz, and then there's a huge spike at 60 hertz because everything is vibrating at 60 hertz. So we have limits on what the asymmetries of the Crab pulsar are, but they're rather weak because it sits on top of this gigantic noise source in our detectors. But luckily, the Crab pulsar is not the only pulsar we know of in the galaxy. There was a targeted search for eccentric, basically elliptical neutron stars in the galaxy, and all the ones we knew about. You know the frequencies. We know how quickly they pulsate. So you multiply by 2, you know the frequency of the gravitational wave you're looking for. And by having such a strong model to look at the data with, you can make very, very sensitive constraints, make very, very sensitive measurements for these gravitational waves from this known pulsar in the galaxy. This here is the ellipticity, the limit on the ellipticity of each of the stars they went after. So this ellipticity is basically a change in the radius over the overall scale of the neutron star. So we're looking for a little tiny hill, this little delta R, on top of that 7-mile radius sphere. And so this kind of limit, most of those limits are put around 10 to the minus 6, 10 to the minus 7 of that changed little hill over the scale of the star. And if you put in the radius of a neutron star, that's a hill of about 1 millimeter. So these gravitational waves are being created. These objects are so incredibly dense, so incredibly extreme, that even a 1 millimeter hill on that neutron star would create gravitational waves that we could have measured. And so 1 million, that sounds like a pretty crazy limit to put on these objects that are pretty distant. They're kiloparsecs away from us. But actually, that's not even that impressive. If you just take the typical equations of state of neutron stars, the typical model for what we think matter does in this extreme of a scenario, 1 millimeter hills aren't really that impressive. They didn't actually think there would be 1 millimeter hills on neutron stars. So this measurement was actually more of a verification. It didn't surprise anybody. It basically ruled out a few very, very extreme equations of state, some very extreme descriptions of what matter might do in these scenarios. So it's kind of surprising. I don't know, 1 millimeter hill on neutron stars.
Well, why would it be a hill?
What's that?
Why would it be a hill on the star?
Right. So first of all, I mean, that's the point. Is that according to theory, according to the description of matter at this high density, we actually think it is very homogeneous. We don't think there's going to be a hill. We can come up with some scenarios where maybe we would think a hill would form. If it's in a binary system, you have some very massive star that's orbiting it and shedding mass onto the neutron star. It forms an accretion disk, and that accretion disk eventually causes the matter to fall in onto the surface of the neutron star. So if that matter happens to pile up, maybe you could create a 1 millimeter hill. We don't think so. We think that the relaxation time is much faster than we would need to create gravitational waves from a 1 millimeter hill. But accretion mechanisms and cracking of the crust and things like that could create 1 millimeter hills. So neutron stars, there's a whole lot of, it's an entire industry of trying to come up with what these things look like and describing that matter as a function of radius from the center of the star. And at the very outer surface, we think that there's this crust that forms in the matter. And that crust can crack, and it creates these jolts, and we can actually see those in pulsars. So we see this very, very regular time, in the pulsar case, 30 hertz wave coming at us, and we can watch it, and it's 30 hertz, 30 hertz, 30 hertz, 30 hertz, and all of a sudden there's a jolt. And it changes by an incredibly tiny fraction of that frequency. It shifts down just a little bit. And so that crack, we think the crust in that case cracked, and just slightly redistributed matter in the star, and it caused the frequency to change, just like a figure skater when they're spinning around in circles, pulling their arms, and it changes the rate that they rotate at. We think that that's happening with these neutron stars. So there's all kinds of things that happen in neutron stars. We don't really know all of the details, and so we're really hoping that there's something that happens that can create these asymmetries that are big enough for us to eventually detect. And so right now, all we have are upper limits. We've never detected gravitational waves from a rotating, isolated neutron star. And so we just watch. The good thing about the data is that as we collect more and more, it gets better and better. And so we just keep putting better and better and better limits on these known pulsars. And as our instruments get more sensitive, we collect more data. We keep pushing those limits to more interesting levels. And we hope that someday we can actually detect some gravitational waves from that. All right, so that was the what we call continuous wave. And we call it continuous wave because it's that fixed frequency. It's just this hum that we measure with detectors. And the only variation that happens in that hum is because the Earth is rotating and orbiting around the Sun. So the antenna pattern, if you remember from my first lecture, looks like a peanut. How we're sensitive to the universe looks like a peanut with these gravitational wave detectors. And so as the Earth rotates, the position of that pulsar moves on that peanut and changes the amplitude of it because we're getting less and more sensitive to it. And so we get this overall modulation of this sine wave. But other than that, it should be this fixed frequency, and that's what we're looking for. Another type of source are these things that we've touched on periodically, these compact binary sources, or just a binary star system in general. Now, the system that we detected was a binary black hole system, and here's that nice simulation that we saw before. We have two black holes orbiting up here. The smaller one is about 29 solar masses, the big one about 36 solar masses, and we saw about the last 5 cycles or so of their orbit as they eventually collided with one another and formed this final black hole. Now, this is the theoretical strain that we would expect from such a system. You'll notice that those of you that have looked at this sheet or looked at the figure from our paper, you'll notice that there seems to be more cycles down here than on that paper. And so that's a matter of the detector's sensitivity. As you go towards earlier and earlier times, you go to lower and lower frequencies, and the noise in our detector gets overwhelming very quickly. So down here, we're very insensitive to that, and that's where we lose it in the electric noise. And so that when we show those plots, we show the actual measured strain, and because we're getting killed by detector noise, it goes off very quickly. Okay, so that's the theoretical thing. There was a numerical simulation of what those two black holes look like. Now, if you notice the time axis down here, that whole window, that was about consistent with the simulation up here in this gravitational wave, it was about 0.3 seconds. So we can replay that at real speed where we don't slow down the simulation. And that was what happened. So 30 solar masses here, rotating around each other 5 times in 0.3 seconds. A whole ton of mass moving really, really quickly. That's what we're looking for, and that's why this gravitational wave was so easy to detect. It's an incredible amount of mass, and it creates this incredible amplitude. 10 to the minus 21. It's still pretty tiny, but it's incredible by gravitational wave standards. That's how we detected this thing. And so because the sound isn't great from the projector, you can't hear it, but there was the sound playing at around 50 hertz, which is really hard for projector speakers to play. All right, so now we can change the mass. Those were 2 really massive things, actually more massive than we expected based on measurements of black holes we've done so far with electromagnetic astronomy. This is the other end of the mass spectrum that LIGO will be sensitive to. So instead of having 2 black holes, we have 2 neutron stars. The time axis here is incredibly different. So this is 80 seconds here, and that is about the overall time that would be sensitive to the gravitational waves from a binary neutron star. And so the frequencies that we're sensitive to, the frequencies that we're getting from this measurement are basically the same as for the binary black hole, but because of the details of the evolution of that orbit, it spends a lot more time at frequencies just above that seismic wall, just above the seismic noise in our detectors, and it spends a long time there. So it's almost a sine wave down here, and then it gets, as those 2 neutron stars get closer and closer together, they start to progress to frequency faster and faster and make that chirp. Now this is a higher frequency, hopefully you can hear it. And I don't play for 80 seconds, don't worry, it's just the last 30 seconds or so. Fine, sorry. So it was playing that whole time, but down here, the frequency is partly low and the speakers aren't great at playing it, but the amplitude is also very low. And so that signal, if you were to look at the same kind of time frequency, those spectrograms that we show of the event, you wouldn't see the signature. It's buried in the noise. And the only way we can measure is by doing these very, very long timescale integrations with a model of what this thing looks like to pull out all of that signal down there. And so a future lecture, I'll go into more details about how we analyze the data and how we can actually pull out these incredibly low signal-to-noise components of gravitational wave signals. But what you heard was basically the last few seconds as it progressed through from 50 or 60 hertz up to about a kilohertz. And so that goes to much, much higher frequencies than the binary black hole system like we detected before. So that gives you about the 2 ends of the spectrum for compact binaries that we expect to detect in LIGO. These are very low mass things, these binary neutron stars, which we have yet to measure. We're very excited to measure it because we will learn completely different things about the universe with measuring these types of mergers versus the binary black holes that we mentioned before. Things like the description of the matter in a neutron star, the equation of state, how that matter behaves at such extreme densities have imprints on this gravitational wave. So if we can make very sensitive measurements of what the gravitational waves look like from these things, we can learn about how matter behaves at very, very high densities. And so we can do almost laboratory type experiments, extreme density behavior of matter on an astrophysical scale, which is pretty cool. Yes?
What do you mean by how matter behaves under these densities? Can you give an example?
So the equation of state is basically describing the pressure of matter as a function of its density. So as you get matter more and more dense, the pressure, the internal pressure of that matter gets higher and higher. But the exact functional form of that is something that we have many different theories for, these different equations of state. And the actual functional form, we hope to eventually put constraints on gravitational wave measurements. But these are all at densities that are way too extreme to be able to produce in the lab. And so the only way we hope to probe matter at these densities are with measurements of neutron stars, like the gravitational wave signatures. Yes?
This may not make any sense, but I am thinking of how the gravitational wave from the center of the star to the outside, how that could be detected, the gravitational wave from the force of that gravitational wave from the center of the star to the edge of the star.
Yes.
That's something.
Yes, so that's exactly the kind of information that we're looking for. By having the details of how that matter is distributed through the neutron star are decided by this equation of state. So the pressure is a function of density. And the exact details of that will change the last final cycle or two of the gravitational wave, which is what we're looking for. And so the other thing that we can hope to do is not necessarily have those different features imprint themselves on the gravitational wave. Sometimes it's the other direction. So sometimes by having all this gravitational radiation within the binary system, you can excite different resonances in the neutron star. And so if you can excite these resonances, so a resonance is like this, there's some natural frequency that you can describe the vibration of something with. And if you can excite it at that frequency, it gets very big very quickly. So if you've had driving in a car and you get to just the right speed and you hear something rattling, that's exciting its natural frequency, that's a resonance. With neutron stars, we think we might be able to have those same kind of resonances, where you have these gravitational waves sweeping through frequencies, and you excite the neutron star, you create this resonance, and what that does is it takes in some energy. When you excite this resonance, it's taking in a whole bunch of energy, and that will cause a jump in the wave frequency, and the frequency of the gravitational wave. So that's a very measurable effect, if it actually happens, and so that's something we could hope to do with a slightly different picture than just imprinting the features of the distribution of matter on the gravitational wave itself. Yes?
Are we pretty sure that a neutron star is all neutrons, not some particle for the core?
It's kind of a misnomer. So there's also protons in there. The exact fraction, we don't really know. We think electrons be pushed out, which is why we call it this nuclear kind of equation of state. But, yeah, so it's not just neutrons, it's mostly neutron stuff.
Question?
Yes?
So what you showed before, the two black holes, that was like 10 to the minus 23, but this strain is 10 to the positive 23?
Yeah, so that's what I meant there is I'm multiplying by a factor of 10 to 23 to get this scale here.
Okay.
So I might have made a mistake on the old one. It's still incredibly tiny, yeah, sorry.
Okay.
That would kill us, I think. That would be bad.
That would probably overload the
At the very least, yeah. Okay, so that's compact binaries. Another source class that I put up there was burst. And so this is basically a catch-all for things that we don't know. Compact binary mergers are kind of a burst-like source. It's this thing that just shows up as a transient phenomenon. It just happens for a very short duration amount of time in our detectors. We call things bursts if it's not a compact binary and it has that behavior. It's just some burst of gravitational waves that doesn't look like a compact binary merger that we measure in our detectors. So one possible source of burst gravitational waves are supernovae. And we call them a burst because we don't have a great model for what the gravitational waves look like from a supernova. So we may not be sure that what we saw was a supernova when we see it, but this is a numerical simulation of a supernova. And this is the gravitational wave that this simulation thinks would be produced by a supernova. So that was a very weird thing. I'll play it one more time. Okay, so that's something. That's gravitational waves. It doesn't have that chirp-like sound that we're looking for. That makes it kind of problematic to detect. We see things kind of like this in the detectors fairly often. There's all of these transients that happen in the detectors that are just noise. So there's some electromagnetic fluctuation, somebody sneezes in the control room, we can get bursts of gravitational, a strain on the detector that looks like that. And it's not gravitational waves, it's just vibrations of the instrument that are looking like gravitational waves that we're trying to look for. This is part of the reason why we have multiple detectors in different parts of the Earth. We hope to separate noise sources so that the chance occurrence of two things that look just like this at just the right amount of time between detectors is very, very low probability. So we have searches that look for burst-like gravitational wave events, and the way they search for them is by looking for this matching characteristic behavior in two different detectors. So again, supernovae are one type of burst source. It's a catch-all. This is our eyes wide open search. It's not as sensitive as our compact binary search because we don't have a model for what this thing looks like. But we can use the information collected by all the detectors to try to search for these types of sources. And this is where it can get really exciting. This is where we're going to find things that we didn't expect. And so this is going to be incredibly exciting in the future. Any questions on the burst before I move on? Yes?
The amplitude went up and then down and then up again, unlike your
Yeah.
Is there a reason for that?
It's really all in the details of this numerical simulation. So you can have all kinds of bounces and things happen as you cause this explosion to happen in a neutron star. And so you get a little explosion, it hits some phase transition in the star's material, it gets kind of reflected a little bit, and you get this bouncing effect. It's really complicated, which is why we don't have great models for what it looks like. And even just looking at different numerical simulations of these explosions, you get a huge range of behavior out of these explosions. Some don't even think it's asymmetric enough to create gravitational waves that we would hope to measure. But all in all, these things are not as extreme. I mean, the overall energy is extreme. Supernovae are very energetic things, but in gravitational waves, they're pretty unimpressive. So we can only hope to detect supernovae that are very, very nearby. Within our galaxy, maybe the next few galaxies over, but not beyond that. Not at the types of megaparsec and gigaparsec scales that we can measure with compact binary things.
Does the direction that you're picking up that particular wave make a difference in the signature?
That's a good question. I don't think so. I think that it's all kind of washed out, but I'm sure that there's some preferential emission of gravitational waves, like they'd be stronger in one direction versus the other. Maybe perpendicular to the explosion would be the most sensitive place to be. But I don't know. I haven't actually thought about it. That's a good question. Okay, so those are bursts, and now we're going to move on to something completely different, stochastic. These are really cool gravitational waves. Stochastic gravitational waves is basic. It's not any one particular source. It's the flood of a population of sources. So we've been talking about, for example, compact binary mergers. There's one set of ripples in a pond. We can measure those waves from that one event and learn about that particular event. But on a universe kind of scale, we have more than one event. We have all kinds of events happening, all kinds of pops going off in the universe. And once you get far away from any one particular source, you don't detect just a single source, but you detect this like combination of sources. And as you get more and more events going off and you're further away from any particular event, all you see is just this rumble from all of the events going on in the universe. And so that's the stochastic effect that we're looking for, the stochastic background of gravitational waves. And you can imagine, anytime you've been in a crowd of people, you can hear maybe one or two conversations going on right around you, maybe one really loud person a few people over. But then after that, you just hear this kind of overall rumble, this hum of people around you. And that hum, that overall rumble is the stochastic background that we're looking for, but in gravitational waves, not people. And so this is an example. This is a simulation of what the stochastic background for a population of binary black holes would look like. And this is something that we are now starting to learn about. We haven't detected a stochastic background yet, but we have detected an individual source. We detected GW 150914. That's a 29 on 36 solar mass black hole binary merger. And now we know that we're not special. That's a very fundamental assumption in astronomy, that we're not special. That we're not close to just the only source of that type that exists in the universe. We just got so lucky as to see it. We know that that's indicative of a population of sources like it in the universe that create this ripple, this overall hum of the universe in gravitational waves. And that's what it sounds like. Does that sound like anything you've heard before? Cosmic background noise. I'm not so young as to not remember what static on a TV was. White noise. I might be the last generation. But that white noise, this overall Gaussian-like noise with some power spectrum, this is kind of white. It's got a little bit of a slope to it. There's also things like red noise, which is like ocean waves beating on shore, and then there's pink noise, which is a really high kind of whiny frequency to it. This is kind of white, but it's noise. It sounds like noise. And our detectors are great at measuring noise. And so it's really, really hard to make measurements of noise on noise. And so this is something that we're now starting to inform based on starting to probe those individual sources that happen to be very near us. But as we get more sensitive, as we collect more data, we can push deeper and deeper into the noise. We get better characterization of the noise of our instruments, and we can look for odd components of it that aren't described by noises we know are in the detector, and are this kind of stochastic background sticking out. So this is a constraint on what the stochastic background could be based on our measurement of GW 150914 and the analysis of those first 16 days of coincident data we collected with our instruments. So x-axis. Down here is 10 hertz, over here is 100 hertz, the log scale. And this is the overall level of the stochastic background. And then here is this blue solid line is the spectrum of a stochastic background. So it's not quite white. If it were white, it would look exactly flat as a function of frequency. It's got some slope to it, some power law slope. And these parabolas here are the sensitivity, up here is the sensitivity of the instrument during our first observing run. This is the real thing. And then down here, these dashed lines are projections for the next observing run. And then this is the 05 observing run, so 4 observing runs later than what we've collected so far. And that's the sensitivity to the background that we would have. So as we collect more data and as the instruments get more sensitive, we can push down to smaller and smaller levels for that stochastic background. And then in pink here is the projection for what the stochastic background could be based on what we learned about binary black holes in the universe from GW 150914. And so there's uncertainty here because we don't have an estimate of the rate that's very consistent, or that's very certain. So this is decided by how often per unit volume, per cubic megaparsec, events like GW 150914 happen. We only measured one. And one does not a rate make, so we need to wait for more to get a better estimate of what that rate is, and that will tighten the error bars on what the stochastic background is going to look like, and then we can have a very good idea of when we're going to be sensitive enough to detect it. And so we can also look at, as a function of observing time, how sensitive we are to this stochastic background. So again, the pink here is the projection for what the stochastic background looks like based on GW 150914. And then in blue here is the SNR, the signal-to-noise ratio of that signal that we're looking for. And as we collect more data, it gets better and better. Each one of these jumps is the instrument getting a little more sensitive, and then that overall progression is just the effect of collecting more data. And so here is a 1 sigma detection based on the signal-to-noise ratio. Here, the middle line is a 3 sigma detection. And then the very top is that magical 5 sigma, that arbitrary evaluation of significance that we usually feel confident in making claims of detection with. That's something passed on to us from our particle physics colleagues at CERN and other places that look for these 5 sigma detections. That's considered extreme enough in this bell curve of nature to call a real detection. So we have this arbitrary threshold that we use like everybody else, and that's where that magical 5 sigma is. So based on these uncertainties, we could get very early, if there happens to be a lot of gravitational wave production from binary black hole systems, we might get really lucky and detect the stochastic background in 10 months or so of collecting data. If we're unlucky, then we have to wait for these later times where this pink is over here, meeting in with the signal-to-noise ratio of these thresholds. And so anywhere from 10 to say 100 months until we detect the stochastic background. This is something that it's not really clear what it's going to teach us. The details of how that stochastic background behaves, looking at that frequency scaling, that gives us an idea of the distribution, the mass distribution of binary black hole mergers. But beyond that, it's just a power law. That doesn't contain much information. So time will tell what this actually looks like and what it can teach us about the universe. But with time, we get sensitivity and hopefully a detection. So that covers all of the sources that we're looking for right now with LIGO. All of the sources of gravitational waves we can imagine, and then that catch-all first category of things we can't imagine, the thing that's going to be really exciting. Not to say that compact binary mergers and other things won't be exciting, but that's going to be the next frontier, hopefully. With that, I'll take any more questions you have. And I know I pushed up a few questions at the very beginning when I was working with sound and wrestling, so please don't hesitate to ask me a question. Thank you. Yes?
Okay, so I want to go back to your comment that a strain of 10 to the plus 23 was choice.
Okay.
So it could be, which I presume you never expect to find.
Yes, because we still exist. It hasn't happened in a very, very long time.
But playing with that idea, if there's a fatal threshold and we were to detect something that was a little lower than that, that would make me a human sensory detector in some sense, I would suppose. So how would it kill me, or how would I feel? Would my head get stretched and squeezed, or?
Every part of your body would get pulled apart from every other part of your body. It's basically like an extreme tidal effect. So one picture that's painted often is what happens to a person as they fall into a black hole. And the thing that kills you is the tides. It's this differential pull of gravity in one direction versus the other. So when you fall into a black hole feet first, your feet experience a stronger pull of gravity than your head, so it stretches you out. So it's spaghettification. When a gravitational wave passes through you, it's like that, but not in a preferential direction. It's pulling you in every direction. Well, actually, pulling you in one direction, squeezing you in the other, depending on the way it's hitting you. So it's pretty gruesome. You get tall and skinny. Well, so if it's passing through you this way, you get tall and skinny, and then you get fat and short. Except not in a clean way. So 10 to the 23, that's multiplying your, if it goes into this way and it's stretching you up first, that's increasing your height, it's multiplying it by 10 to the 23. So it'd be pretty explosive. So yeah, that has not happened. And that is very certain. Yes?
The LIGO instrument, one of the arms lengthens. Does the wavelength of the photon also lengthen?
It's a messy picture. We really need to go into full field equations to describe the behavior of the instrument. What happens is, the speed of light is constant. So if you think of them as photons, they travel at the same speed, regardless of whether a gravitational wave is stretching the instrument or not. And so the time it takes for a wave crest or a photon to travel the length of the arm and back will change as a function of time. So the wavelength does get stretched out, but the behavior of the light is still the same in many ways because it travels at the same speed regardless of the stretching or squeezing of the local speed.
So it's kind of like a red shift and then a blue shift.
Yeah, you can think of it that way. So the wavelength does get expanded and contracted, but the speed of light is constant. So you still have the time of arrival of light crest, which is basically the temperature. Yes?
So you've got a wave going through space. Where does it end up?
Sorry, we have a wave going through space. That was the question.
Where does it end up?
Where does what end up? The gravitational wave?
Gravitational wave.
So the gravitational wave travels unimpeded by matter. So it can travel through dust in the galaxy. It can travel through intergalactic mediums without any effect. And so it just travels on for infinity. The amplitude always falling off, the distance it travels. So eventually it just gets lower and lower and lower in amplitude. It merges with all the other gravitational waves that are coming from other parts of the universe at that very low amplitude. And that's what's creating that stochastic background that we're looking for. But it just creates this overall hum to the universe, this overall very spread out power of gravitational waves.
Do we know if gravitational waves interfere with each other like light?
So there's standard waves, at least in the linearized form. So when you're far away from the source of gravitational waves, they behave like classical waves in many ways, and part of that is interference. So you can, if you somehow got two sources of gravitational waves conspire and create exactly out-of-phase gravitational waves, then they would cancel each other out. Luckily, the universe isn't that mean to us, but it could theoretically happen, yeah. And so one thing you kind of think about, the one type of scenario where I can think of at least that might happen is if you have lensing. So I mentioned lensing at one point with the general relativity lecture, where you have some big concentration of mass in between you and some source of light. It causes this lensing effect of the light, this Einstein rings and things that you can create around that very massive object. You can get lensing of gravitational waves too. And so if you have some half effects that happen to conspire just the right way, you split that wave up in half, it goes around the big massive body, and then they come back together out of phase or create interesting interference patterns. Yes?
I figure if I ask this question often enough, someone will screw up and give me the answer that I want.
That's not a great way to have questions.
In a classical wave, as waves go, is that actually a compression wave?
Sorry, say it again. Is our gravitational waves compression waves?
In a quadrupole wave, is that really a compression wave?
I think thinking about it in that way doesn't quite make sense with general relativity because it's a higher dimensional thing, the stretching and squeezing of space and time in every direction. So it's kind of a compressional wave, but it's not in the way that sound is. So sound, I mean, is just this compression wave through air molecules that arrives in our ears. It's always a contraction and expansion in this opposite direction of the direction of travel. Gravitational waves are kind of like a compression wave, except that they stretch and squeeze space-time in every single direction. There's no orientation of direction based on the direction of travel. So it's kind of like a compression wave, but not quite in the classical sense. Did I mess up? Yes?
That was the answer I was looking for.
The time when you stretch speed based on time, how is light constant?
So so you're saying that. Sorry, say that again.
Speed of light be constant.
How can the speed of light be constant? So that is a great question. That is a fundamental assumption of special relativity. I wouldn't say that there's a very satisfying underlying reason for why that's the case. But making that assumption, it creates all these crazy effects, time dilation, and all these other things that come out of special relativity.
So how can we assume that speed is constant? I mean, speed of light is constant.
So if the speed of light weren't constant, then we wouldn't get the time dilation effect that we can measure with atomic clocks. So you can think of it from an experimental point of view. That if you can pose that question: does light travel at a constant speed for all observers? And if you make that assumption, you can make all these measurements with atomic clocks. You can raise a foot off the floor, and you get a measurable dilation of time. Time passes for something that's 1 foot off the ground versus on the ground.
So it's just more of a measurement.
So it's definitely a point of measurement. From general relativity, maybe there's more fundamental reason why the speed of light is constant. You can think of it as that's just how light behaves because it's a massless particle according to general relativity. It has to travel at the speed of light for every observer. So I guess it's less of an assumption in general relativity, but in the end, it's just how energy behaves. So if you think about accelerating a particle, you apply some force to a rocket, it gets faster and faster and faster, and you put in some amount of energy to make it go faster. As you get closer and closer to the speed of light, the amount of energy you need to put in to make it go 1 meter per second faster goes through the roof. And you get up to 0.9999 times the speed of light, it takes almost an infinite amount of energy to get it another 0.000001 meters per second faster. And so there's this very, very real effect of the speed of light, that if you have something with mass, it takes an infinite amount of energy to get it to go to the speed of light. So there's the speed of light is something very special that the universe has given us. And there's all these experimental things that back that up, but it's a weird thing. It's weird to think of the speed of light being a constant for every single observer, no matter how fast it's moving. And so that's why the effects of special relativity and general relativity are so weird.
So everything else is squeezed and stretched except for light.
Yes. Yes.
Okay.
Yes.
Something a bit more concrete. So about gravitational waves from supernovas, you showed this simulation, which I recognize as a flash simulation since I was at Flash Center.
Yes.
And then you played a sound to it.
Yes.
So I wonder how did you derive that sound?
The sound was from a completely different simulation that was from a group that was kind enough to share the results of the gravitational wave strand. So the physics are slightly different between those, I'm sure.
And then the other thing is you didn't pursue that simulation even to the point of detonation, which is really where things
that was where the movie ended. That was posted online, so I would have happily taken it further if I could. But
yes, they take so long, so we don't always do them until the three things explode.
That's computers aren't cheap. Yeah, you had a question.
Black holes are causing spinning, right?
Yes. Yes, overwhelmingly yes, and that's something we're really excited to do. We made measurements already on the spin of GW15 on I-14. They're just not very interesting. So the effects of spin are a couple of different effects. It matters the orientation of the spin, so the orbit. So if you have these two black holes orbiting one another, if the spins of the black holes, if they're rotating and the axis of rotation is exactly aligned with the orbit, with the orbital rotation, then the effects of the spin are kind of hard to measure. What it does is it affects how they inspiral, how quickly they inspiral. So So if you turn the knob on the spin, if it's a line, you change that frequency progression of the gravitational wave. And something else can do that. If you turn the knob on the mass ratio, you make one thing more or less massive than the other. It causes that same effect. So there's a very real degeneracy between how we can constrain mass ratio and how we can constrain spin. Now, you get to a physical limit with the spin, eventually they become, with the mass, they eventually become equal. And so that kind of limits the effect of that degeneracy. And so with those things in mind, we can put constraints on the spin of GW 150914 just through modeling of the gravitational wave based on how we know it behaves with spin. The other effect of spin is if you misalign those spins, then you get transfer of angular momentum from the spin of the black holes to the orbit. And you create this precession. And so you can get the orbital plane itself wobbling. And then because the strength of the gravitational waves changes as you change the inclination, you change the angle of the orbit that you're viewing, you get this modulation of the overall amplitude of the gravitational wave. And so as that wobbles, it gets stronger and weaker. The gravitational wave that we see gets stronger and weaker. So that breaks that degeneracy. That's a very different effect than mass ratio. And so if we're lucky enough to observe gravitational waves from a compact binary merger with two black holes that are spinning and they have a misaligned spin with the orbital angular momentum, and we happen to see it kind of edge on, we can make incredibly precise measurements of everything, of spins, of mass. We can really characterize that source, and so we're really, really excited for something like that. But GW 150914 was not that. It was a very smooth chirp. We didn't see any of those amplitude modulations from precession. So the spins are only, we constrain them. We know that they're not high and misaligned. The only way that can happen is that there are very special configurations that limit the amount of transfer of angular momentum between orbit and spin. But yeah, so we can definitely put constraints on black hole spin through gravitational waves. And I would say much cleaner constraints than we can do with general astronomy right now. So we have already put constraints on spin before GW 150914 with electromagnetic observations. But the way they do that is they need a black hole in an X-ray binary system where you have a massive stellar companion that's dumping mass onto the black hole. When that happens, you get this accretion disk. And all that matter settles down to this nice thin disk that's falling into the black hole. As it gets closer and closer to the black hole, that matter in the accretion disk is heated up, and it glows like the filament of a light bulb. But this light bulb is so hot it emits any X-rays. And so if you can do very, very detailed modeling of the emission of that accretion disk from the very center all the way out to the edge, so you have to know that how that temperature profile behaves, how that creates radiation, and then you have to do all this very complicated ray tracing of that radiation in strong field general relativity. Then you can model the power spectrum of that light, and then you can try to figure out what the spin of the black hole is, because that has some very small imprints on it. So it's a really tough measurement. Tons and tons of modeling needed to do it, and we don't know for sure the details of accretion disk behavior. So I would argue that the constraints from gravitational waves are by far the most trustworthy and the least plagued by systematics. So that's going to be, I think, one of the very interesting things we can do with the next few events that we're doing. Yes? Then you.
You had two merging Neutron stars.
I should say, we're definitely over time, so I will not be insulted if you want to go out and enjoy the story. So otherwise, I'll hang around for a few more minutes and answer the questions. Yep.
Very powerful magnetic field.
Yep.
Was it any way make gravitational different one and really merging down?
Okay. So the question was, neutron stars have this incredibly strong magnetic field. Does the interplay of those magnetic fields have any imprint or any impression on the gravitational wave? And the short answer is no. We don't think so. So the magnetic fields are strong in a astrophysical sense, but weak in a real sense of actually having an effect on how these things behave. So first of all, the magnetic field itself has no effect on gravitational waves. And the only effect that it could possibly have is just affecting how those two orbit around one another. But the fields are way too weak to do that. So it does have implications for electromagnetic counterparts. And so how those things merge, how their magnetic fields merge together, the effect of that on the emission of the light coming from matter, all come into play. And that goes into like gamma ray burst territory of we're hoping to see gamma ray bursts coming from. We think that things we call gamma ray bursts, incredibly short duration bursts of gamma rays, are caused by the merger of compact objects like neutron stars. And the details will depend on magnetic fields along with the level of it. Yes?
With inflation that produces gravitational waves, it might someday distinguish from that.
Yes. So the very famous, eventually disproven claim of gravitational waves recently was the bicep measurement. And so it didn't get as much press as the LIGO thing, but they basically claimed to have made measurements of the imprint of gravitational waves from the Big Bang that are imprinted on the cosmic microwave background. And so the effect that it actually has is this very characteristic pattern in the polarization of the cosmic microwave background. And those are caused by these cosmic gravitational waves, this overall background from the Big Bang and inflation. So that they do hope to make that measurement, but right now they haven't. But that's something that is at a completely different frequencies, different part of the gravitational wave band. Very, 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 very low frequencies, and something we could never measure directly. The only thing we could do is hope to measure it in great stuff that happens directly. Yes?
On that note, can gravitational waves be reflected in any way?
I don't know. I don't think so. It wouldn't be a reflection in the classical sense, because I can't think of any boundary that you would have that would be able to repel gravitational waves. You could have a lens. I mean, you could have a lens of mass that could maybe pull it around and back, but I think you have to have a really weird distribution of mass. So I think that incredibly most likely no. Maybe you can come up with a theoretical way to do it, but
is that the only way that it would not be reflected then?
I don't know. I don't even know. Sorry. Yes.
So the measured strain in this event was something at a factor of 10 to the minus 22. So that's at this distance. What about some arbitrary distance in the neighborhood, let's say a light year away?
Yep.
Can you work out what the strain is at those kind of nearby distances?
Yes, exactly so, because we measured the strain for this one. We know how far away it was, and we know that the strain scales like 1 over distance.
And so
by moving it closer, it changes proportional to the distance.
Well, what's the number when you're real close? So just pick any distance.
Well, if it's 100 times closer, that's 100 times more. That's stronger. So the question, you can go to the extreme and say that you're 1 AU away from that event. You're 1 Earth orbital radius away, and you can measure the strain, and it's actually not that large of a number. It wouldn't be that 10 to the 23 that would rip you apart. It's something that you may feel as it passes through you. Maybe at most there's some coupling in your eardrum, but it's surprisingly not that bad. They were just 1 AU away. It's pretty interesting. Yes? Last question.
Well, one of those sources of that make up your expected statistical effect, would that be just lack of mergers, or also the long time before the merger itself?
Yeah, so
does it also include neutron mergers?
Everything would be involved. So anything that creates gravitational waves would be involved. The exact effect would be dependent on the amplitude of the waves coming from that event. So binary neutron star mergers have lower amplitude waves, so that you would be less sensitive. You'd be basically sensitive to shorter distances of all of the sources that you add up to get that stochastic background. But in the end, all compact binary mergers contribute some kind of effect to the stochastic background. But if you get too extreme in mass, kind of direction.